cooling. So as we are using our computers, they're generating a lot of heat. We have heat that is generated inside the power supply as it's doing the generation going from AC to DC. That generates a lot of heat. Our processor generates a lot of heat as it does all the mathematical computations, as well as our graphics cards. Those are our three main heat sources inside the computer. And so as we generate all this heat by thermal radiation, because of the electromagnetism that's going through the circuitry, our CPUs, our GPUs, even our hard disk and our optical drives will generate some heat, and our power supplies. If you're in a hot environment, it's going to be harder for your computer to work to get rid of this additional heat. So if you happen to be living in a hot area like, I don't know, Florida or Arizona, and you have your computer or your laptop sitting on the back deck of your house, it's going to be working a lot harder trying to cool it down. So the effects of heat, right? If you have a lot of heat, what's going to end up happening? Well, one thing is that your components can actually turn themselves off. If your motherboard gets overheated, it will. Most BIOSes now will shut down the computer to protect itself. Same thing with the CPU. It might slow down to try to generate less heat to keep it operating, or it may shut down completely. Your entire system may shut down. Most often, though, you're not going to notice a huge performance decrease, but your components can become damaged by overheating if you're not reducing enough heat, and this can reduce the lifespan of your components. We talked about this with overclocking back in processors. Yes, you can overclock your processors, but if you don't remove the heat that's associated with it, that processor is not going to last as long as it normally would. So how do we reduce the heat? Well, the first way we do it is we use heat sinks. They can be used to increase the surface area of the processor and remove the heat away from those surface components. Here's an example of one. This green metal portion, this radiator fins, is a heat sink. And then sitting on top of it, we have a fan to draw the heat up and away from the processor. These are usually made out of aluminum alloy or copper because they have good heat transfer capabilities, and they can be combined with a cooling fan to give you much more effectiveness in removing that heat. Your case design is also going to be important to maximize your airflow and reduce heat. If you're having one of those really high-powered systems or gaming machines, they make special cases that have a lot of airflow, lots of holes in them, to let the air come through the case and out the back and get it away. Also, you want to make sure your cables are not bundled up on the back of your case, because that will reduce your airflow as well. You want to make sure things are open and fluid in there. So your BIOS can actually be set up to help dissipate some heat as well. A lot of BIOSes have what's called PC health or temperature monitoring. When we did our BIOS lab yesterday, you guys saw that. We were able to see how hot our CPUs were running. There's a sensor in there that if it gets too hot, it'll start spinning that fan up faster. Most of us, our CPU fans were running at around 3600, right? If we looked at Sarah's, hers was going up into the 4000, 5000s because her CPU was hotter, right? The case fan was the same way. Based on the heat generated in the case, most of ours were operating around 750 RPMs. Sarah's machine was overheating, and so it was trying to go at 1000 RPMs. And so we have to have these fans. They're going to boost up higher, try to get more airflow going through there. None of the other settings in the BIOS are going to do much to reduce the CPU power consumption without simultaneously reducing your performance. So if I drop the CPU power consumption, like on a laptop, it's going to reduce less heat. But if I have high performance, it's going to generate more heat. My laptop's a great example of that. If I'm doing things like just showing PowerPoints, not a big deal. My fan doesn't kick on. It's got enough passive methods of passive heat dissipation. But as soon as I start running virtual machines, I start increasing that processing power. It starts kicking on fans to try to cool down my system because it's starting to generate more and more heat. So we have three different main types of cooling that we talk about. We have active cooling, where we combine the heat sink with a fan. We have passive cooling, where we rely on the heat sink only. Or we have a complex system called liquid cooling that's going to utilize pumps and tubing and cooling plates to reduce the temperature of the system. And we have the three examples here for you. On the top, we have the active. The middle, we have just the passive. And the bottom, we have an example of a liquid-cooled system. So how do you install and maintain your cooling systems? Well, the first thing we do is we put the CPU, the processor, in the slot on the motherboard. Next, we're going to apply the thermal paste, which is a chemical compound that's going to increase the heat transfer from the processor to the heatsink. Next, we're going to put on the heatsink. And finally, we're going to put the cooling fan on top. That's a traditional system for using an active cooling system. If you're doing liquid cooling, it's a little bit different. We'll talk about that in a couple of slides. The location of the case fans is also important. On our particular machines, we only have one case fan. Some machines have 2 or 3 case fans. These particular cases can support more case fans if you're generating more heat. The case fans are necessary because they're going to remove the hot air from the components. A lot of our components in the computer don't have their own fan, so the case fan takes all that heat out for them. Basic placement, you're going to see the bottom front of the case near the drive bays, where they'll suck the air into the machine. Using that fan, they'll have a rear fan on the top, and behind the CPU to exhaust that air that comes in and take it out. And sometimes on the sides of the case, they'll also use that as a way to intake air for the CPU as well. In our particular one, we only have the exhaust fan in the rear, right? You guys saw that when you open up the case. Again, if you're using a gaming system, you're going to have lots and lots of fans to do lots of cooling, or you're going to switch to a liquid-cooled environment. How do you install a case fan? You're going to remove a faulty fan or install a new fan. Basically, you need a Phillips head screwdriver. That's all you're going to need. To replace it, you're going to remove the old one by unscrewing it. You're going to unplug the cable from the header or the Molex connection, depending on if it's plugged into the motherboard or plugged directly to the power supply. To install the new fan, you're going to hold the fan in place with one hand, screw the 4 bolts in, and then you're going to provide power to the fan by connecting it back to that header or that Molex connection. When we talk about the header, it's the one that goes directly to the motherboard, the 3 pins. Some fans, if you're putting them in your motherboard doesn't support that, you'll plug it directly to one of the 4-pin Molex connectors from the power supply. So, different types of connectors for our case fans. We have the 3-pin power connectors. We have the 4-pin power connectors, which gives you a 4th pin that does speed control. So most of the newer fans are going to have 4 pins because they actually will speed up or speed down depending on the heat levels in the case. Or the old style one is that Molex connector. And you can see that right here is an open Molex connector, right? Just to give you an example, and you can see on this one, we have the processor fan sucking the heat upward, and then the rear case fan sucking the heat outward of the case. So, liquid cooling. Water has a very high thermal conductivity. It's a pretty good heat transfer method. Water will absorb heat better than air does. So we use liquid cooling as a way to take away more heat than just using air cooling. Liquid cooling also is influenced less by the ambient temperature. So if I'm working in a hot environment like the desert, liquid-cooled systems are going to hold up better. Where air-cooled, I'm much more susceptible to what the air that I'm sucking in already temperature is. So if I'm in a 70-degree server room or a 90-degree backyard, I'm going to have a much better performance of air-cooled in a 70-degree environment. With liquid-cooled, it's really not going to make a difference either way. The water cooling, the way it works, or liquid cooling, it works by basically running water over your components. Now, we don't really use water in computers. We're using this oily chemical substance in liquid-cooled, and it's going to transfer heat from each part to a radiator that's going to dissipate the heat and keeps the water cool, just like your car engine's radiator does. It's how your car keeps its engine cool, is it runs the radiator fluid through the radiator, removing the heat as it goes through the car system, comes back to the radiator in the front, and the air cools it over that radiator to remove the heat from the water. So your liquid-cooled system, you have 4 basic parts that you have to have. You're going to have a radiator, which is essentially the mount that goes on top of the processor that the water will come in and out of. It's going to be the radiator is where the heat is removed. The water block is what sits on top of your processor, and the water comes in and takes the water. The heat comes into the water. The water is then pushed to the radiator where it is cooled down. You have the pump, which pushes the water around the system, and a reservoir, which is an extra collection mechanism for additional water, because these systems are never 100% perfect, and you might lose some water through evaporation or heat dissipation, and the reservoir will fill that back up for you. Your expected heat output and desired temperature range of the components will dictate what kind of cooling parts you're going to buy. So as you pick out your system, you're going to have to do some research and go, oh, well, this processor needs X amount of cooling, therefore I need to buy this particular system. So how do you install these? You're going to ensure the CPU is inserted in the socket, just like we did before. We're going to clean the CPU and the water block of any kind of dust and debris. We're still going to use thermal paste between the processor and the water block like we did with the heatsink before. And then we're going to attach the radiator to the case. Usually it goes in the place where the rear fan was. And then you're going to connect the reservoir to the radiator and connect all your piping together. Good things about liquid-cooled systems: they have unparalleled cooling performance. They can dissipate a lot of heat for you. They increase the lifespan of your components by keeping them cool and operating at peak efficiency. If you're doing overclocking, liquid-cooled is pretty much essential. And the other thing is they're really quiet, so they're not noisy like fans are. The only thing that's really making the noise in the liquid-cooled system is the pump, and the pump is fairly quiet. So instead of having 3 or 4 fans blaring away, you can use liquid-cooled to give you a quieter operation. Which if you're going to do something in like a home theater environment, or if you're in a dorm room and you want to make sure you're not too noisy for your neighbors who are trying to sleep, liquid-cooled can work well. So if you have a home user's a PC with an overclocked CPU with a relatively small heatsink and small fans on the 800-watt power supply and a high-end video card. So what does that sound like to you guys? Sounds to me like lots of heat, right? 800-watt power supply is going to generate a ton of heat. The overclocked CPU is generating a ton of heat, and the high-end video card is giving you a ton of heat. What should you recommend to manage the heat more efficiently? Should we replace the CPU heatsink with a high RPM or revolution per minute fan? Should we purchase an energy-efficient power supply? Should we not overclock the CPU, or should we use a liquid-cooled system? D. The best way to give this guy efficiency is going to be give him a liquid-cooled system.